So in my opinion, I think this gas law we're about to talk about, Avogadro's law, is perhaps the easiest one to understand conceptually. It's the easiest one to visualize, but it was not obvious to the chemists and scientists back several hundred years ago. And in fact, it started off as a hypothesis, and then it was later shown to be, in fact, true. But Avogadro's law states the following. It originally was a hypothesis, like I said. Okay, and so Avogadro's hypothesis, it went like this: equal volumes of gases at the same temperature and pressure contain the same number of particles. Okay, now why is that so hard to believe? Because have you ever seen a molecule? Have you ever seen an atom of helium? No, you haven't. They're way too small. So it's kind of a striking idea, but here's an example of Avogadro's hypothesis. Imagine you have a liter of, so this is 1 liter, and it's got helium in there, and let's say it's at 750 torr and 25 degrees Celsius. Okay, and so this gas sample would be very, very light, you know, and obviously you can't see the particles in there because they're way too small. But this would almost be floating away like a balloon or something is filled with helium, right? And so then over here you've got a nearly identical box, but this box contains 1 liter of carbon dioxide at 750 torr, and it's also at 25 degrees Celsius. Okay, these boxes, according to Avogadro, would contain the same number of particles. Okay, and yet they don't weigh the same at all. Okay, this one is very light. It would tend to be like floating away if this was just a plastic cube or something. Very light, kind of floating away, like helium does. Okay, if this was like a plastic box or something, it might just float away. Whereas if it was carbon dioxide, it's actually much denser. And so just have no problem staying on the table. Okay, so in one sense, these gases seem very similar. Same volume, same pressure, same temperature. But they do contain different gases. This one, very, very light. This one, kind of heavy. And so Avogadro had this interesting idea. He says, since they have the same volume, temperature, and pressure, they have something else in common, and that's the number of particles, even though we can't see them. And so now it actually gets very interesting because, you know, if you start wondering, why is this box heavier than this box? You might infer that these particles are lighter particles, even though you can't see them. Okay, and so Avogadro's hypothesis actually was one of the major things that allowed chemists to start determining the weights of atoms, the molar masses of the elements on the periodic table. It kind of broke open the door on the mystery of what makes elements different from one another. But started off as a hypothesis, and it was later shown to be a law. So equal volumes of gases at the same temperature and pressure contain the same number of particles. Okay, so these are helium atoms over here. These are carbon dioxide molecules. Okay, so there's actually 3 times as many atoms over here, but each one of these little red dots I've drawn is a carbon dioxide molecule, and that's considered a particle. So there are the same number of particles of gas bouncing around in here than over here, as over here. So why is this important? Because it shows that there's a direct relationship, a directly proportional relationship between the moles of a gas, the number of particles, and the volume. So moles and volume are directly proportional. Okay, provided you keep the same temperature and pressure. So at a constant temperature and pressure, Avogadro's law is going to apply. Okay, if you think about those 4 variables that gases have, they exert pressure, they occupy some volume, they have a temperature, and they are made up of particles. Avogadro's law, we're focusing on volume and particles, and we're holding these constant. Okay, and so hold pressure constant, hold temperature constant, and then we can look in a controlled way at the relationship between volume and the number of moles. Okay, so each one of these gas laws we've talked about, Boyle's law, Charles' law, Avogadro's law, there are particular variables that we're looking at in a controlled way as we hold the other ones constant. Right? In Charles' law, we're holding pressure and moles constant, and in Avogadro's law, we're holding pressure and temperature constant. Okay, and quick graph of what this would look like. As long as you have constant temperature and pressure, what's going to happen to the volume as the number of moles increases? By the way, for moles, the abbreviation, or the symbol rather, for the number of moles is the letter N. N represents the number of moles, and Avogadro's law tells us that as the number of moles increases, the volume is going to increase linearly. So this should be a line here with a constant slope, just kind of going straight up. All right, and so again, if you start off with a particular number of moles, and let's say you double that number of moles, you're also going to double the volume. So if you have N1 and N2, you have V1 and V2 right there. Okay, so have a linear relationship. And we can express that like this. The volume divided by the number of moles is a constant. And the more convenient form of Avogadro's law is V1 over N1 equals V2 over N2. It looks a lot like Charles' law, the form of the equation with the fraction. Okay, so let's have a look at these problems down here. A 25.5 liter balloon holding 3.5 moles of carbon dioxide leaks. If we are able to determine that 1.9 moles of carbon dioxide escaped before the container could be sealed, what is the new volume of the container? Okay, we are assuming, even though it doesn't say it here, assume constant pressure and temperature. Then Avogadro's law applies. So our first number of moles is 3.5. Our first volume is 25.5 liters. Our second number of moles. Okay, so to determine that, we want to know what's actually in the balloon. If you think about it, the balloon started off with a volume of 25.5 liters, and then if a certain amount escapes, right, it says 1.9 moles of gas have escaped. That means we've lost 1.9 moles. That's not what's left. So we need to take 3.5 moles and subtract out 1.9 moles, whatever that is our resulting number of moles, and that will allow us to find the new volume. Okay, so of course 3.5 minus 2 would be 1.5 plus 0.1 back in. That's 1.6 moles inside of here. Okay, and so we've got 1.6 moles in there. We had 3.5 moles in there, so we can determine the new volume of the balloon. Less moles, less volume. So let's plug in what we've got. V1, N1, V2 over N2. And we're going to solve for that new volume. Rearrange the equation. We've got V1 times N2 over N1. That's going to be V2. Okay, so the first volume is 25.5 liters. And then the ratio of our moles, 1.6 over 3.5. So that ratio of moles multiplied by our original volume gives us our new volume. 25.5 times 1.6 over 3.5. And rounding to two significant figures, right about 12 liters. 12 liters. Okay, so that's how Avogadro's law can be applied when you have a situation where some things are changing. And again, just to recap, directly proportional relationship. For the honor students, I want you to continue on watching the follow-up video on Avogadro's law.